I'm from the Functional Organic Materials and Devices group, which is in chemistry, so it's a little bit different than our last talk. And for many times, I think we're in the same world but very different planets. When I talk about trying to bring some of our organic materials into, let's say, the built environment, the level of scale starts to get very impressive. On the left side, they talk in tons. On the right side, in our labs, we make milligrams or grams of material. But what I want to do, we all know that chemistry surrounds us everywhere. What we're sitting on, the wall color that we're looking at, all came out of a chemistry lab. So what I'm doing is trying to take these materials that we make over in chemistry here in very small vials and try to bring them into the built environment and see if we can control light. What my first research is been working on is what are called luminescent solar concentrators. So these are actually for energy generation to start with, but they're very simple things. They're just plastic plates filled with a fluorescent dye. Sunlight enters the plate from the top surface, gets absorbed and emitted at a longer wavelength. So green light goes in, red light comes out. You can see that it gets brighter along the edges, and here we can place a solar cell, for example, to generate electricity. So this is what we started with. These are inexpensive things. They're colorful, adaptable. They're pretty tough, so you can drop them, whack them, things like that. You can't do that with, for example, a silicon cell. It would completely destroy them. They work in both sunny and cloudy conditions. So I have some photographs here of some objects that already exist in our environment. A bridge near Den Bosch and a museum in Spain. The designers have already chosen, they want something colorful. They want something that will give a nice visual impression. But at the moment, these aren't doing anything else. Well, the sound barrier blocks sound, but essentially that's all it does. What I want to do is give it function. So we can either generate electricity, or as some of my compatriots in Australia have done, they also use luminescent concentrators. But instead, they place them in a case with 3 panels here, red, yellow, and a blue. Sunlight gets absorbed by these panels. Then they can travel the light along fibers, through the walls, through the floor. Then at the end of the line, you can then mix the colors again and get white light. So this is a day lighting system, but rather than having to directly bring it in with a light pole, you can do it using luminescence. So essentially the same thing that we do here, but instead of a solar cell, we just directly use the light. Now some of the advantages are also in the artistic realm. So please excuse the poor artwork because we're only scientists. But we have a plastic plate here, and we have some color paints. And all we're going to do is just color onto our plate. We have a solar cell, in this case, on the side, with some wires coming off it, and a little motor here with a little fan. Already you can see some of the light reaching the edge here, and I think probably among the artists out in the audience, you can already think of images that you can make that also will have function. These can also generate power. Right? So you can take a piece of artwork and generate power with it, give it an additional function. So this is the kind of thing that I'm interested in. The background of our group is actually completely different than this. We were in liquid crystals for many, many years in the form of making, actually many of your laptops probably have materials that were worked on by some members of our group. So cell phones, video screens, projectors, all these type of objects that are very common around us. Well, I want to use liquid crystals in the built environment. And people think, well, how can we adapt this type of system to the built environment? Well, the first thing, I should talk a little bit about liquid crystals and why we're interested in these materials. A liquid crystal is essentially a material that has phases that are intermediate between the normal crystal phase. For example, water, when it freezes, forms a crystal, where you have 3-dimensional order, where all the molecules are in specific locations and rigid. They can't move. Normally, when you warm a crystal, it turns into a liquid. That means all the molecules can flow, but there's no order, no direction. Well, intermediate to that, there are some materials called liquid crystals that have a mesophase. The molecules tend to be rigid rods, something like this pen, with a floppy tail on the end. These rods tend to line up with each other, all facing the same direction, but they can slide past each other, allowing flow. So, the nice thing about liquid crystals is that in a very simple way, with a surface treatment, I can line these molecules up in many different ways, and they will spontaneously form these different orderings. For example, planar. I can make them all lie down facing the same direction. Or I can get them all to stand up on a surface. Or lie down and then go to a stand up on the other surface. Or even twisted through a depth of a material. And I can do all this with a simple surface layer, and then I lay it out from solution, and will spontaneously form these layers. Now, if I also take this floppy tail I described, and I put a material such as an acrylate on it, I can expose it to light and cause a cross-linking. So I can turn my liquid into a solid film. And that solid film contains all the information here. So all the order is maintained. Okay, why can we use all this? Well, first I'm going to just talk about a system in the liquid phase. And this is for controlling essentially the lighting within a room. So we have a window, and you normally know we have to draw a curtain or raise the curtain to change the amount of light coming through. What we want to do is to make this something that we can automatically respond to the environment and be able to run itself. So essentially this is a video screen, much like the laptop that I have right here. In a laptop you have liquid crystals that can basically form a couple orientations. In one orientation, they block your backlight from coming through in a very simple way. Another position, it allows light through. We're doing the same thing with these windows, except we're putting in a fluorescent dye as well. The fluorescent dye also is a long, thin molecule. It follows the liquid crystal, so in this orientation, it absorbs light. But not only absorbing it, then emits light. So just like these luminescent concentrators, light is being emitted, goes through the window pane to the edge, and we can generate power with our window. We can use that power then to switch the position of the liquid crystals, and in this orientation, the dyes go this way and they don't absorb. So we can get a light state and a dark state, and the window can run itself. Now, the benefits of this, of course, are you can have a room where you put a meter on your table, said, okay, during the day, I want exactly this many lux at my tabletop. Cloud comes over, person walks by, the rain clouds come and then go away. All of it can be regulated by your window, and you can have standard lighting conditions at your table. So there's none of this problem of drawing the blinds, and when the sun comes out, you forget to raise them again. However, this has been worked in a spin-off, Pure Plus, from the university that's trying to commercialize this, but there's still improvements to be needed. So you can see that our on-off ratios aren't perfect, for example. We have to get the colors right. We have to find out what colors people like in their window, for example. So we try to now go, instead of being electrically addressed, we also want to make systems that can respond to other triggers in the environment. The temperature, or perhaps the color quality. For example, later in the day, there may be more red light in the surroundings. So, responsive windows or walls for light redirection. So we know near the window you often have a lot of glare, and you might like to spread the glare around the window deeper into the room. So what we try to do are generate materials that can respond to either wavelength or heat and form structures. Those structures then could redirect the light. I have a little film here of some materials that are developed. So this is a liquid crystalline film. This is the heat source. So as you bring it near this heat source, the film will respond to this by changing its shape. This one we've made just a 4-lane film, but it's possible to do 8 lanes, it's possible to do checkerboards. You can get patterns that will raise up as a cone, fold up almost like a box. So there's a lot of options on the forms. And if you look at it from the side, you could also start thinking, is that a lens? Could maybe make a lens form, this type of thing. We can also try to make a relief structure. So now you can imagine on your wall that you'd like to have maybe it's a smooth surface, but when the sun strikes it, perhaps we get things to come out of the surface that allow scattering or distribution of light or something of that nature. So we've taken liquid crystals in each of these different lanes, one of them which will essentially swell when exposed to a particular wavelength, other ones that contract. So if you put that together, whoops, if my video will work, you can get, at least in an animated form, something like this, where you can get surface relief structures that will pop out in response to particular stimuli. So we can tune this for particular wavelengths. We can tune it to a particular temperature. We can make it addressable electrically. So this type of thing is a possibility, but what I'm looking for are what are the applications, or what could people use this for? You could also think in terms of a responsive scattering system. So let's take a window now. The temperature is rising. The sun comes out, but it's only incident on part of the window. So many systems that exist now, you can have the entire system go dark, for example, but perhaps you only want the top of it to change into a scattering state. We can have a material then that could go through a phase change, possibly heat driven, that will cause it to start to scatter light. Now, we're not the only people to work on this type of thing. There's a group called Sante that is now soliciting funds on a Kickstarter campaign, if anyone's interested. But what they are doing is, where's my cursor? There we go. So this is a little app that they have on their iPhone, and they can change the transparency of their system, and they're driving it with electricity. And they're also showing that they can project the video directly onto their window. So they turn it into the scattering state, and they can direct images onto it. Again, instead of having this type of system, you can have one that you can easily direct and completely change the transparency. Now what we'd like to do is make this autonomous, something that can respond to either a temperature or a light quality and have essentially the same sort of effect. As we talk about light transfer through a window, another feature that we'd like to find a solution for is the heat. During the summertime, it can get quite hot indoors when the sun is shining through, so most of the time people pull the curtain, turn on the lights, and then when the sun goes down, they forget to open the curtain again, they leave the lights on. The next day they come to the office, they just turn on the lights, forget to open the curtain, and so forth. We would like to have a system that can sense when the infrared level is at a certain height and then selectively reflect the infrared while allowing passage of the green light. We can do this using a liquid crystal based reflector. It's called a cholesteric liquid crystal. This is something that we can tune to any specific wavelength we can reflect. And what we're working on in the lab in a DPI project, Dutch Polymer Institute, we are trying to be able to tune this to specific temperatures. So maybe we have the onset at 32 degrees, for example, or when there's a certain light quality that we, as a trigger, that will tell us we need to switch it. So now I'm going into a room, and if the people that were here early saw our poor technicians had to climb up on this table to try to readjust the positions of these lights. Something that we think would be very nice to do is if we can address these from a distance to change the direction of the lighting. So, for example, my little model here could use a little UV pointer or something of that nature, change a structure on the surface of that light to change its position. So we have some examples of materials from the laboratory down here. This is a UV light source here, and we have a film, and when you turn on the light, it actually turns and bends towards the light. So then you could imagine, could we make a little light conducting fiber, for example, wrap it in this liquid crystal, and then as you address it, you can bend it to any particular position that I'm standing. Even nicer, well, potentially nicer. Let's say this is one of our luminescent light sources that's got the white light, but then you decide, well, I would really like to highlight this dress in the shop in red or in green. We could also make a diffractive surface structure that would pop out of the surface and perhaps only bring out the red light. So these are all sorts of ideas. Many of them are in various stages of being worked on, but they have not been brought to the real world. What does this need? This is main interest for me to come to this type of meeting. Well, for one, industrial partners and building designers to help define these needs and generate these research goals. We have lots of things that we can study, but if they don't have an application, then it feels a little bit in a void. We need, in my side, is to develop materials and dyes, but also the application method that has to be suitable for upscaling. I don't work with any materials that you really can't just buy off the shelf. I could, for example, with these devices, get world record efficiencies and get a nice paper, but the materials that I use would be so expensive that would have no way to be produced on a large scale. So we're really trying to keep this into an approachable range. But most of all, there really needs to be interdisciplinary communication. What do I mean by that? The people, somebody that's interested, for example, in a window that reflects infrared, they have to tell me what conditions do you want them to switch at. Do you want it at 35 degrees, 38? Do you want it under red light, blue light? If you're going to have a window that switches, the coating that I put on there, what does the burn rate have to be, for example? These are things that I don't know, but they're drivers for the research. And I would very much be interested in talking with anyone that has a project or has a need in the lighting area that you think that we might have something in here that could be useful to get some feedback. And let me know what you need, and then we can talk. So I just have a few people I have to thank. Colleagues at SFG, that's quite a few people, but these are some of the ones working on the topics I talked here. We have some industrial partners, funding from STW and DPI. And finally, afterwards, I would certainly love to hear your questions and comments on this, and if you think we're going in the right direction. Thank you.
Okay, thank you.